Hi everyone, today we're going to be talking about igneous petrology, specifically silicate magmas. AKA we'll be talking about how volatiles like water and CO2 can be dissolved in magma and how they can affect the explosiveness of volcanic eruptions. We're going to be talking about magmatic viscosity, how viscous or thick and resistant to flow magmas can be and how that can affect the explosivity of their eruptions. And then we're going to be talking a little bit about partial melting and magmatic mixing and differentiation and all of the things that come along with silicate containing magmas, which is every magma. So first, I just want to discuss a little bit of the difference between basaltic and silicate-rich magmas. Every magma has silicate in it. Silica tetrahedra is what basically holds together all geologic material. But like we talked about in the classifications video, I'll link it up here if you want to check it out. There's felsic and there's mafic igneous rocks. Felsic magmas that cool to create felsic rocks are really silicate rich or silica rich, SiO2. And mafic magmas, which form mafic rocks, are less silica rich. So they still have silica, but they have much less silica than felsic magmas. And so when we say silicate magmas, we're talking about all magmas, but also focusing on the side of more felsic, silica rich magmas. And then basalt magmas is going to be the focus of another video in this igneous petrology playlist when we go over basalt and mantle structures. But in this video, we will be discussing concepts that apply to all magmas, basaltic, felsic. So the concepts we discuss in this video are universal in terms of the trends, the effects of viscosity and temperature and composition and partial melting, and all these things apply to all magmas. And the last thing I want to just mention before we really jump into this video is the main difference, or the main reason that we differentiate rocks and magmas based on silica content. So if you look at this figure to the left here, we can see the difference between rhyolitic or felsic magma eruption to the surface of the earth versus andesitic or intermediate magma eruption at the surface of the earth, and then basaltic or mafic magma eruption slash just oozing out of the earth. And the reason these are different, or the reason this basaltic one seems more flowy and the rhyolitic one seems a bit more explosive, is because of viscosity, which is highly affected by composition, which comes back to silica content. The higher the amount of silica in the magma, the more thick and viscous the magma will be, and the more explosive the eruption will be. The lower the content of silica, which is shown here to the right, what we see here is that the silica tetrahedra are broken up by network modifying ions, these big black dots. That makes the silica tetrahedra less polymerized, aka less long chains, because these network modifying ions modify the long chains of silica tetrahedra and therefore break up those silica tetrahedra and make the magma more flowy or less viscous. This means basaltic and mafic magmas that have less silica content, or at least less silica polymerization, are more flowy and don't create very explosive eruptions. And then obviously we can see in the intermediate case for andesite, it is intermediate between the two. It's kind of flowy, but it's also kind of explosive. But let's get into some of those concepts that I said apply to all magmas here. So this is the role of volatiles. Volatiles, what are volatiles? Well, they're things that can evaporate easily. So volatiles like water and carbon dioxide, which we know can either be dissolved in liquid form or escape as gases or vapor, these volatiles, when present in magmas or dissolved in magmas, can really affect how the magma behaves in terms of its eruptions. And the reason this is because it affects the network of silica tetrahedra. If you haven't watched any of my mineralogy videos, specifically the crystal structures one, I talk a little bit about silica tetrahedra. Silica tetrahedra is just a silicon atom bonded to 4 oxygen atoms in a tetrahedral shape. And these silica tetrahedra bond to each other, more silica tetrahedra, and make long chains called polymers. These silica polymers polymers, or these silica chains, they are what make up the framework of magma. And these silica polymers can be broken apart by water that enters and dissolves in the magma. This water attacks the bridging oxygen atoms, or the oxygen atoms that connects to silica tetrahedra, and it breaks them apart and replaces it with an OH group. You don't need to understand the chemistry here. All you need to know is this water breaks apart the polymerization. And we know that if you break apart the polymerization, you lower the viscosity. You make the magma more flowy, and the eruption will be less explosive. Whereas CO2 enhances polymerization of silica. So it kind of brings together the silica tetrahedra and makes them bond or bridge their oxygens and therefore form long chains. And so this would increase the viscosity of the magma. So let's look at how this affects the magma's movement through Earth, its eruptions, etc. So we know we just said that water decreases the viscosity of magma because it decreases the polymerization. But what about when magma is within Earth? What does water do? Well, water, for example, the water brought down underneath the surface of Earth by subducting plates, promotes melting of this underlying material, which is actually why we get volcanism at subduction zones. Because the water promotes this melting, the magma then melts and rises to the surface and forms volcanoes. This is ultimately because water lowers the melting temperature of rocks. This we talk about in the phase diagram video. I'll link it up here if you want to check it out. But not only does water affect the melting temperature of rocks, it also affects the crystallization of magma. So often water saturated magmas will cool and crystallize before they even reach the surface. And so they don't even get to erupt out of the surface in a volcano. They're so saturated in water, they just crystallize under the surface. But when they do reach the surface, they cause really explosive eruptions. And so we can see an example of this here. Why this is, we're going to talk about when we get to viscosity, because it gets really, really cool how volatiles can make really explosive eruptions. And same goes for carbon dioxide. Even though it does the opposite in terms of polymerization with magma than water does, it also causes more explosive eruptions. And this effect of water and carbon dioxide, as well as other volatiles and magma to create these explosive eruptions, all roots from the fact that they want to be gases at atmospheric or surface pressure. So what does this mean, and how might the viscosity of the magma play a role in causing these explosive eruptions? So let's get into viscosity, because this is where it all comes together. If you're unsure right now why gases create these explosive reactions, don't worry. After these next few slides, you will completely have a light bulb go off in your brain, because when I was making these slides, I also did. So viscosity, it is the resistance to flow, aka water is super flowy and therefore not very viscous. Honey is not very flowy, therefore pretty resistant to flow, and is highly viscous. So really quick, before we discuss magmas, let's talk a little bit about soda. What does soda have in common with magmas? Well, we know it contains carbon dioxide, so that's one thing. Let's talk a little bit about how shaking a bottle or can of soda can be analogous to a volcanic eruption. If you shake up a can or bottle of soda and then open it, the pressure decreases immediately when you open it. And this decrease in pressure allows the CO2 that was dissolved as a liquid to escape as a gas in an eruption of soda, because this liquid to gas conversion greatly increases the volume of the soda, or in our case magma, and drives it out of whatever opening it's allowed to go up or through. And so that is the same driving force that causes magma to rise and explode out of a volcano, is this conversion to gas by volatiles in the magma, increasing that volume and driving that magma up whatever crevice it can get out of. So obviously I just kind of said this, but same goes for magma. It rises, pressure decreases as it reaches the surface, and gas tries to escape, increasing the volume of the magma, which drives the magma upward in a violent eruption. But if the gas is allowed to escape easily, the eruption will be somewhat quiet. If the gas has a hard time escaping, the eruption will be insanely explosive. This is where viscosity comes into play. So here, let's consider a low viscosity magma. The gases can escape pretty easily, like they would if you were blowing bubbles into water. I don't know about you, but when I was a kid, and maybe a little older than I should have been, I loved blowing bubbles in my chocolate milk. So when I did this, the bubbles would escape somewhat easily if I blew hard enough. But now imagine doing the same thing, but instead of chocolate milk or water, you're blowing the bubbles bubbles into honey. What would happen? Would those bubbles be able to escape as easily? No, they would not. Same thing goes for highly viscous magma. This magma would trap its gases for long enough to really increase that volume to cause really crazy and explosive eruptions, whereas the less viscous or less silicon containing magmas would allow that gas to escape more easily, like water or chocolate milk, and it wouldn't be as crazy of a volume increase, and it wouldn't be as explosive of an eruption. Moving to what controls viscosity in magma. So we just talked about how viscosity can control the eruptions, but what determines the viscosity of magmas? Two main factors that control viscosity are temperature and composition. Increased temperature typically decreases viscosity. Moreover, in terms of composition, which is probably the main controlling factor on viscosity, we talked about how highly polymerized magmas, or magmas with really long chains of silica tetrahedra, are much more viscous than magmas with silica polymers that are all broken up because of network modifying ions. So we can see both this temperature and composition trend in the bottom right figure. What we see is that the more high temperature and lower silica content magmas have much lower viscosities and flow a lot more easily. These are mafic and intermediate, or basalt and andesitic magmas. And then we see with dacite and rhyolite, which is felsic, these contain a lot of silica, aka are highly polymerized in their silica tetrahedra because they don't have as many network modifying ions, and because of this they're highly resistant to flow or highly viscous. Moving on to density. Density affects magma's ascent velocity, how fast it can ascend through Earth and to the Earth's surface, the settling of crystals in magma, which we'll talk about in a second, and ion diffusion. Ion diffusion actually highly affects grain size of the rocks that cool from magmas, and we talked about ion diffusion in the rock textures video, so I'll link it up here if you want to check it out because I won't go too much over it now, but it does affect how fast ions diffuse through magmas and can cause larger grain sizes if that ion diffusion is fast and smaller grain sizes if the ion diffusion is slow. So that has to do with grain size, but the point here is that density plays a large role in determining magma behavior as well as the rocks that cool from the magma. So what do we know about density in magmas? Well, we can see here a list of common substances that you probably know of, like water, rubbing alcohol, corn syrup, molasses, and honey, compared to magmas, which all have their densities listed here, and the density of magmas is greater than that of these other materials, but it does range quite a bit from around 2.2 to 3.1 grams per milliliter density. So what controls where magmas fall in this range of density? Well, density rises with increasing pressure and falls with increasing temperature. And a good general rule to know is that mafic magmas are typically denser than felsic ones. So just the opposite of viscosity, which is lower in mafic magmas and higher in felsic magmas, density is higher in mafic magmas and lower in felsic magmas. And it's for a pretty obvious reason. Mafic magmas, if you remember from my igneous rock classifications video, have a lot of heavy elements like iron and magnesium and calcium, and felsic magmas have much lighter elements like potassium and sodium. And so the fact that mafic magmas contain these heavier elements or heavier oxides, in the case of calcium oxide and iron oxides, this means that the magma of mafic material is much more dense. And we're going to move on now, but don't worry, we're going to talk about this figure behind these two text blocks here in a few slides. I just wanted to point out that density affects the crystal settling in magmas. So we just talked about a bunch of properties of magma, like volatile content and viscosity and density, and how that affects the magma's behavior. But now let's get into the actual magma's behavior. Magma differentiates under Earth's surface, and that controls what magma actually reaches Earth's surface and cools and forms rocks that we go and find. So we need to understand a little bit about magma differentiation to understand what that rock's journey was, what source it came from, what composition the source was, etc. So let's talk a little bit about partial melting, which is a key factor in controlling what magma actually reaches Earth's surface and cools to form the rocks that we go and ultimately find and examine. So partial melting in general just means the fact that when material melts, it doesn't all melt at the same temperature or, for that matter, time. The magma may reach a high enough temperature to melt some of the material, typically at grain boundaries. We talk about why this occurs at grain boundaries in the phase diagrams video. video, so you can go check that out. But this will start at grain boundaries, and some materials will melt at lower temperatures than others. Just like, if you boil a pot of water, that will boil at a different temperature than if you try and boil something else. Or if you freeze ice, it'll freeze at a different temperature than if you try and freeze something else. So all materials have their own respective melting and freezing temperatures. For this reason, rocks, which contain a lot of different minerals, a lot of different materials, melt at different temperatures. And so when the temperature becomes high enough, certain material may melt and certain material may not. And this is called partial melting. Now, equilibrium melting is nice because what happens in equilibrium melting is you start to melt everything, it partially melts, and then it goes all the way to completion without the liquid that had melted in the beginning escaping from the system. So everything stays in the system until everything is fully melted, aka the final liquid that was resulted from the melting is the same composition as the original solid that was melted. Whereas fractional melting occurs when the partial melt is removed incrementally. And so the final liquid is very different from the starting solid composition because the partial melt causes some materials, typically felsic materials. If a rock contains both mafic and felsic material, the felsic material will melt first just because of how thermodynamics works. And the felsic material, if incrementally removed, for example, at this subduction zone, shown here to the bottom right, the magma then rises as soon as it melts and it goes to the surface to create this volcanism here. If the magma is rising after it melts, what will be left behind is a mafic residue. And this mafic residue will have to reach much higher temperatures to be able to melt. And this may or may not occur. Let's imagine a magma chamber. This green thing is the magma chamber. And what's a magma chamber? Well, if we look at the last scenario, we can look at these blobs here. These blobs are magma chambers. And if they cool under the surface, they're called plutons. And we talk about how plutons and plutonic structures like dikes and sills can form and cool under the surface in the plutonic structures video. I'll link it up here if you want to check it out. But these magma chambers, when still melted and containing magma, have differentiation occurring within them. And the reason this is because of partial melting, and typically fractional partial melting. This is because if a magma chamber contains both mafic and felsic material, and therefore also intermediate material, and it's all mixed up, once it starts to cool down in temperature, these materials will differentiate because of differences in crystallization temperatures of different materials, as well as differences in density. For example, we can see the denser, more mafic material that contains all those heavy elements like iron and manganese and calcium is going to settle to the bottom of the chamber, whereas the felsic material is going to stay in the upper part of the chamber, which felsic material is not only less dense, but it also takes a lot cooler temperatures to crystallize out of solution and settle to the bottom of the chamber than mafic material does. So we just talked about how in terms of melting, felsic material will melt first and mafic material will melt last. It takes higher temperatures to melt mafic material. Well, the same is true for crystallization except switch, which makes sense. So the mafic material will crystallize out of the cooling magma before or at higher temperatures than the felsic material will. And the felsic material will need cooler temperatures to allow it to crystallize out. That's why the crystallization as well as density of the mafic material allows those crystals to settle down to the bottom of the chamber, differentiating the magma's composition from the bottom to the top of the chamber, allowing mostly felsic material and maybe some intermediate material to rise up out of the chamber into the surface to come out of volcanoes and cool as rocks. Therefore, this brings us to this key concept. All partial melts are more felsic than their source rock. So if you have volcanoes having magma come out of them, it's incredibly likely that they are the result of partial melting, and therefore that magma that's coming out of the volcano, I guess once it comes out, it's lava, is more felsic than the source rock that melted to form the magma that it came from. So all partial melts are more felsic than their source rock. So I know we just kind of discussed crystallization, but let's just show one more example here because I really like this figure and it shows a really, really easily understandable little series here of crystallizing. So we talked about partial melting and how equilibrium melting and fractional melting differ on the last slide, but I also just talked a little bit about cooling. So crystallization can also occur just like partial melting in either equilibrium crystallization or fractional crystallization. Equilibrium crystallization is exactly like equilibrium melting in that all the final solid is the same composition of the original melt. So when you have a liquid magma magma or melt, what you're going to get in the solid as it cools is the same composition as the melt, and that's because nothing's leaving the system. However, fractional crystallization, like we just showed in that little magma chamber thing, is more often the case. And this is because crystals are removed by gravitational settling, causing changes to the composition of the remaining liquid. So what do we mean by this? Just what we showed in the previous figure, just kind of a different figure to kind of switch things up and make sure you understand. The olivine crystallizes out of the solution at higher temperatures. It doesn't take that much lowering of the temperature to get olivine to crystallize out. And then it settles to the bottom by gravitational settling. This makes the remaining liquid in the magma chamber more felsic. And at this intermediate point, around 900 degrees Celsius, a little bit cooler than the olivine crystallization temperature, you'll get the crystallization of pyroxene and a little bit of plagioclase feldspar, and this is getting rid of that last bit of mafic material and bringing it to the bottom, laying it on top of the already there olivine. Then the pyroxene and plagioclase go on top of it, and then finally you change the liquid even more felsic and you lower the temperature even more, and finally all that plagioclase feldspars as well as whatever else is in there will eventually crystallize and settle to the bottom as that magma chamber cools. So here's a question: how do we know what order this crystallization occurs in? How do I know that olivine cools and crystallizes at higher temperatures than does plagioclase feldspar and more felsic material? Well, this is all because of Bowen. Bowen's reaction series, I'm sure you've heard that word if you're watching this video, is the key to understanding the order of what will crystallize out of magmas, or likely what will melt out of rocks first. And so the temperatures at which this occurs is different for more mafic material versus more felsic material, as we've been discussing. And Bowen's reaction series is something I go over in one of my really early videos called Igneous Rocks and Bowen's Reaction Series. If you want to check it out, I'll link it up here. But it's pretty simple. It's just an experimentally determined order of the temperatures at which these things will crystallize from the liquid. The last few things I want to discuss is magma assimilation, magma mixing, and how this affects magma differentiation. So magma assimilation is just when the host rock is torn off and incorporated into the rising magma. What do I mean by this? Well, this is a zoomed in square of this larger scenario down here in this cross section. What we have is some sort of country rock that this magma is coming up into. And as it does so, it's going to tear off some of that host rock that it's coming up into and incorporate it into its own magma. This can change the magma's composition if it melts completely and gets incorporated into that magma before it rises. And magma mixing is when two chambers kind of glob together and mix their magmas, because not all chambers are created equal, guys. Magmas can have very different compositions and their chambers even right next to each other depending on their source. And if they mix, then they mix and they become a new composition depending on how mafic or felsic they are and all that stuff. So that's magma mixing, that's magma assimilation, and magma differentiation mostly occurs, like we talked about, when fractional crystallization occurs. So say you rip up a host rock and assimilate it into your magma, or say you have magma mixing between two chambers. Once cooling starts to occur and crystallization begins, you're likely going to get fractional crystallization, and you're going to differentiate that magma chamber based on what's settling to the bottom and leaving the remaining liquid enriched in whatever is not settling out to the bottom. So that's it for silicate magmas and volatiles, magma mixing, partial melting, viscosity, density, and all of the things we discussed today. It was based on one of the chapters from Essentials of Igneous and Metamorphic Petrology by Ronald and Carol Frost. So if you want to check out that book or any of my other major or minor references that I'm using to make this and other videos, check out my description below and you can find links for those and you can check them out. Other than that, the upcoming videos include my Chemistry of Igneous Rocks video, which is going to be probably the next Igneous Petrology video we get for this playlist, and then I'm going to try and discuss basalt and the mantle in an upcoming video, as well as stable and radiogenic isotopes and their applications to igneous petrology in another upcoming video. And as you can see, I don't have the thumbnails created for those videos yet, and I don't know what order they will come out yet, but they will be at some point in the future and hopefully help you out. Lastly, if you are still watching this video, comment down below for me if you went and tried to blow bubbles into honey after watching this video. Anyway, thanks guys, and I'll see you guys next time. Bye.